he will introduce them. I just want to introduce Ken to you. If you don't know him already, I think most people in the room do know him. Ken is the founding director of the ANU Energy Change Institute and also the inaugural director of the Zero Carbon Energy for Asia Pacific Grand Challenge initiative of the ANU. And congratulations are in order to Ken. Ken has just been elected a fellow of the Australian Academy of Technology and Engineering. That is, of course, a big thing. And also, Ken is the recipient of the 2021 ANU Chancellor's Award for Distinguished Contribution to the University. So congratulations, Ken. And over to you.
Thank you very much for that kind introduction, Frank. And I see quite a few familiar faces in the audience, many of whom were at the very first energy update, which actually was in 2013. In 2012, it was called Australia's Energy Future. So good to see all these faces back here again. And of course, let me again join Frank in recognising Ian Cronshaw, of course, has contributed so substantially to Energy Update over the years. So this session is looking at hydrogen and zero emissions export industries. And just to kind of motivate this session, I wanted to show you this slide, which indicates some of the work that's come out of the Grand Challenge, which is called Zero Carbon Energy for the Asia Pacific. So just to paint a picture of what the future might look like, Australia, of course, is a major energy exporter. We all know that, LNG, coal, etc. Let's just say that the world continues to need the same amount of energy as we're selling it now out into the future. And if we were to then export not LNG and coal, but renewable-based energy, then the future might look something like the picture here. So if we export the same amount of energy in joules, okay, not in dollars or kilos, but in joules, and let's just say that 20% of that was as electricity through undersea cables, high voltage DC undersea cables to Southeast Asia and beyond. And let's say that 80% of that was exported as hydrogen made from electrolysis of water using renewable energy. Then we'd be looking at exporting 65 million tonnes a year of hydrogen, green hydrogen, and 540 terawatt hours a year of green electricity. Just to give you an indication, the total amount of electricity generated in Australia at the moment is 264 terawatt hours per year. Okay, so that's more than double the amount of domestic electricity through export and a whole lot more, again, through hydrogen. And you can see on the screen the amount of renewable electricity required under each of those arrows. Then let's make another assumption, which is that we mine the same amount of ore as we do at the moment. So that's iron ore and aluminium ore. And we export that as green steel and green aluminium, using renewable energy and hydrogen to reduce the ores and turn it into metal. In that case, we'd be exporting 50 million tonnes of green steel compared to 6 million tonnes of ordinary steel at the moment, and 18 million tonnes of green aluminium compared to 2 million tonnes at the moment. And this would take, again, large amounts of renewable energy. You can see the numbers up there on the screen. If you add all this up, then the total amount of renewable electricity required is 7,040 terawatt hours a year. That is 27 times Australia's present electricity generating capacity. And if you add that to the 100% domestic electricity that we need at the moment, the other 200%, as Frank mentioned earlier, that we need to electrify everything else, then that becomes 3,000% renewable energy. Okay, lots of people talk about a few 100% renewables. If you look at the export picture, where the export tail is wagging the domestic dog, then you can see that the export picture makes this thousands of percent. Even if only a fraction of this is true, these are really big numbers. And if only a fraction is true, then Australia's export future is doomed to be significantly less than it is at the moment. So we have to do at least some of this. Okay, so that sets the scene. I'd now like to invite the first of our speakers up to the podium. And I'd like to invite, first of all, Dr. Fiona Beck. Fiona is a senior lecturer at the College of Engineering and Computer Science here at ANU, and she's also convener of the Hydrogen Project at the ANU Grand Challenge Zero Carbon Energy for the Asia Pacific. So welcome, Fiona.
Thank you. Yes, I'm going to dive right in. So what do we need to do to get to net zero? Frank gave a good presentation on this. And clearly, the most important thing that we have to do is to install a lot of renewable energy very quickly, electrify everything as quickly as possible. But after that, anything that we cannot electrify, hydrogen has a role in the net carbon energy future. So we can make hydrogen from renewable energy, and if we do that, we can start to abate these very hard to decarbonize sectors. So that's things like long-term energy storage, energy export, looking at long-haul and heavy-duty transport, and also fossil fuels, feedstock and fuel for industry, for example, fertilizer, steel, metal refining, and mining. So there are a number of ways to make hydrogen. Currently, all my slides seem to be a bit scrambled. I do apologize. So currently, we make it from natural gas using a process called steam methane reforming. You can also make it from coal and a range of other heavy hydrocarbons. This accounts for about 2% of global emissions at the moment. You can make it from electrolysis. This is a process where you split water using electricity and you get hydrogen and oxygen. Obviously, if you do that with grid-based electricity, given the fact that most of our grids around the world are powered by fossil fuels, that still results in quite a lot of carbon dioxide pollution. However, if you make this electricity from renewable sources, then this can become what we call renewable or green hydrogen. And this has no process emissions associated with it at all. There are other ways that people are looking at for making low emissions hydrogen as well, still based on fossil fuels, using the same processes that we've already used traditionally, but now adding carbon capture and storage technologies to capture some of those process emissions, compress the carbon dioxide, and pump them underground up to 2 kilometers, where they can be stored indefinitely in appropriate geological rock formations. However, the really critical thing here is the emissions intensity of whatever pathway you choose. So emissions intensity is the amount of carbon dioxide and other greenhouse gas pollutants that are released per unit energy of the fuel. So this graph here shows the emissions intensity of a range of different fuels. And you can see there that for all the cases that we are looking at, which includes black coal, brown coal, and natural gas, making hydrogen from natural gas results in more greenhouse gases per unit energy. It's only when you start to apply some carbon capture and storage technologies that you can start to reduce that. However, the graph also shows that the residual emissions can be quite significant. And this is because CCS is not perfect. Typically, with mature technologies which have been tested at scale, you can capture about 50 to 90% of the process emissions. That's not including the energy that you need to transport the CO2 and pump it underground. CCS also doesn't account for any type of fugitive emissions. So those are these solid boxes on top, stacked on top of the bar graphs there. Oops. And what you'll see if you look carefully is, in fact, making hydrogen from fossil fuels increases the amount of fugitive emissions that you end up getting. And that's because you need more of the fossil fuels per unit energy due to process inefficiencies, I should say. And adding carbon capture and storage actually makes it worse because you need more energy yet again. So whatever type of CCS you're using, you're always going to get more fugitive emissions. So at the moment, low-emission fossil fuel-based hydrogen is still cheaper than green hydrogen, quite significantly. So this is an analysis that we did, led by Dr. Tom Longden, who was here. I think he's left. And we did this analysis of a large number of studies, and it's fairly clear that there is still a significant cost advantage to using low-emissions fossil fuel-based technologies. However, there is a clear pathway for the cost reductions in renewable hydrogen. And this is because the costs of renewable hydrogen are determined by the cost of the renewable energy driving the electrolyzer and the cost of the electrolyzer itself. Renewable energy costs have fallen rapidly over the last few decades and are likely to continue doing so. And additionally, electrolyzer costs are very likely to decrease as well. Electrolyzers are a very mature technology. They've been used in industry for a very long time, but they're a niche at the moment. They're not used very widely. If we scale up production to the types of gigawatts that we're talking about to produce renewable energy, there is a very quick learning curve that we will move down, and costs could come down very rapidly. This can't be said of fossil fuel-based hydrogen production, which is already at scale. There's already a 70 million ton hydrogen industry based on fossil fuels. CCS technologies have also been around forever. There's less of a pathway for cost reductions. All of this is to say that in the future, there is a very good chance that renewable hydrogen will be cost competitive with low emissions fossil fuel-based hydrogen. So some very quick takeaways. Renewable hydrogen can help decarbonize hard-to-abate sectors. Developing a new, large-scale, low-emissions hydrogen industry based on fossil fuels will undermine global efforts to reduce methane emissions. Renewable hydrogen has a clear pathway to cost reduction and could outcompete fossil fuel-based low-emission hydrogen in the near future. It's not clear how near. And it's really important to recognize that a lot of definitions of clean and low-emission hydrogen do include both renewable and low-emissions fossil fuel-based hydrogen. And so it's not the label that you have to look at, it's the emissions intensity. Thank you very much.
Thank you, Fiona. So now I'd like to invite our next speaker, Dr. John Pye, or Associate Professor John Pye, from the College of Engineering and Computer Science. John is the convener of the Renewably Refined Metals Project in the Grand Challenge, Zero Carbon Energy for the Asia Pacific. And I'll leave it to John to introduce the topic.
Talking about green iron and steel next, and this is very much continuing from what Fiona's been talking about with hydrogen supply. The role of hydrogen in the evolving steel industry is going to be very important. This little picture on the first slide is the first ever vehicle made from green steel, and this was a highlight from this year. I'd like to acknowledge the other ANU and non-ANU colleagues who've been involved in this work that's been done through the Zero Carbon Energy Grand Challenge here at ANU. Okay, so an outline for my very short presentation. I'm just going to quickly talk about the present iron and steel industry as well as some future technologies, some scenarios about where this might go as far as emissions, implications for Australia, and I'm going to mention the new heavy industry low carbon transition CRC that ANU's participating in. This little inset picture is reminding us about the geography of the iron ore industry in Australia, the mining. It's predominantly the vast majority of our iron ore comes from the Pilbara region, which coincidentally is one of the best regions for solar energy in the world. So the iron and steel industry, looks really complicated when you put all the pieces and steps on a page together. But in a sense, it's quite simple if we're thinking about decarbonisation, because the blast furnace, which is that orange square there in the middle, is responsible for the vast majority of global steel production and also the vast majority of emissions from this industry. So transforming this industry starts with transforming the blast furnace, which currently depends on a feed of processed coal, coke, to fire it up and drive the reaction, the reduction of the oxides in the iron ore, and that's where the vast majority of the emissions happen. There are also emissions in other steps, which I'll come to briefly. But after the blast furnace, there's some downstream steps to eliminate certain impurities and all the rolling and shaping, but you don't have to worry about them so much when it comes to emissions. Upstream of the blast furnace, there's processing that's done of the ore to reduce the number of impurities that go into the furnace, because the things that are in the impurities that go into the furnace then need to be eliminated, and that's energy intensive. So there's a sort of a whole balancing act to get the impurities out of the process in the cheapest way at different stages. Right at the start of this process is the iron ores, and the majority of the iron ore that we use these days are fines, so small particles. They have to be stuck together into lumps before they can go into a blast furnace, so sintering and pellet making. And the beneficiation step, which has various sub-processes, is that removal of impurities. Alongside the fines are lump ores, which are great. You just can shovel them straight into the blast furnace if they're of a sufficiently high grade. The scale of this industry, 2,500 million tonnes per year of iron ore. The largest exporter of iron ore is Australia with 900 million tonnes per year, and the next biggest is Brazil. So just to talk a moment about ores, Pilbara hematite, there's various grades of iron ore, different minerals, but hematite is the big one in Australia and globally. Our hematite in Australia is something around 57% iron. Of course, it depends exactly on the mine, but that's round about where it is. If you go over to Brazil, the Carajás mines, very large, a much higher grade, about 65%. So that's Brazil's strength, perhaps, in the iron and steel industry. And the third one I've listed there is the mine in the north of Sweden, which is being used to drive the green steel project that I'll talk about in a minute. It's magnetite. It's a different mineral. It's only 43% iron, but because it's magnetite, it's magnetic, and that really facilitates low-cost upgrading of the ore. So they can get it up to nearly 70% using a magnetic separation process, which is really important. Right. In parallel with the blast furnace route is the direct reduced iron making pathway. It's only 5% of current production. It's natural gas. It's a bit lower in emissions. And then also important to mention scrap, which is something we need to increase as much as possible in this area. In China, it's only 20%. In the US, it's up to 60%. Very variable depending on where you are. So lots of really exciting things happening in green steel in the last year or so. The HYBRIT process is the leader. It's in Sweden. This is a hydrogen iron making process. They make pellets out of magnetite using biomass. Then they have a hydrogen furnace. And as I mentioned, they've been producing actual products just in the last year. ThyssenKrupp in Germany has been injecting hydrogen into a blast furnace. That is not a pathway to 100% decarbonisation, but it's something that can be done at scale quite quickly. Primetals in Austria's been starting up their fluidised bed iron making process. This is also a pilot scale system like the HYBRIT one in Sweden, but it's also on a pathway to 100% reduction of emissions. And finally, not a hydrogen technology, but also of great interest is what's happening in the US with Boston Metals, and they have a direct, very high temperature electrolytic steel making pathway. And it's early days, but this might be one of the really interesting long-term technologies. It actually doesn't rely on hydrogen, but it's much further from market. The map here, the red dots on that map, I've highlighted the hydrogen-related steel projects in Europe. So you can see it's it's really blossoming. There's a lot of investment, a lot of activity. These are some scenarios that we did here at ANU in the Grand Challenge program. We wanted to consider different rates of reduction of emissions in this industry. And we took it as a starting point that the industry would be responsible for its own emissions. So all of this discussion about CCS and bioenergy, carbon capture and storage, direct air capture, soil carbon, we took it as our assumption for this analysis that this industry would do those things internally rather than sort of separate from the industry. So we've got scenarios which involve CCS here. But for the reasons that Fiona was talking about, CCS struggles to reach 100% a reduction of emissions. It's hard to remove all of the CO2 from these streams. So our scenarios identify, I suppose, that if we really want to get to zero emissions and we want this sector to act for itself, then these zero emission steelmaking technologies need to come in, and they need to be coming in quite rapidly from 2030, 2040 and onwards. The plot on the figure on the right is going a little bit to Ken's points earlier about the resources required to power this industry, because it needs so much electricity to produce hydrogen, to do the hydrogen steelmaking. So if we imagine a hydrogen steelmaking industry at the scale of Australia's current exports, then yes, it needs lots of renewable energy. It also needs lots of materials to build that renewable energy. And some of the materials, for the scale we're talking about, are almost kind of the entire global supply of certain materials for a year. So 70% of global glass production, 80% of global neodymium production, which is the magnets in wind turbines. So this is, I think, doable over periods of a couple of decades, but it's obviously going to put a lot of pressure on those supply chains, and they're going to be of increasing importance. So big questions for Australia in this whole space. You know, Australia, as we've heard, depends very heavily on renewable on energy exports. Metallurgical coal, as opposed to thermal coal, is a huge one, and of course the iron ore. But neither of these markets are secure in the long term. You know, Brazil has that high-grade iron ore. Countries are going to be transitioning to hydrogen. It's entirely possible that we lose both our iron ore and our coal exports. You know, we don't understand yet enough about how iron making will be adapted to our particular grades of ore in Australia. Lower grade ores. We really need to spend time getting across how to adjust the process to be cost effective at scale with Pilbara ores, or we risk losing a really big income stream. So alongside just how the process works, there's a question of whether we can do this in Australia, potentially at that scale. So with large amounts of renewable energy, maybe in the Pilbara, how much of the process would we actually take on? It's possible to produce completely finished steel. It's also possible to produce intermediate products like pellets and pig iron and hot briquetted iron. So we really need to evaluate this in the emerging and evolving energy landscape and the changing costs of renewable energy. And not least of those things would be energy storage, because all of these iron and steel processes run continuously. We can't have a process that starts up and shuts down every day when the sun goes down. And I'm an engineer, so I suppose I've been speaking a lot about technology, but there's so many policy and market issues around this. There are really interesting things happening in Europe with carbon border adjustment mechanisms and the possibility that they might drive this industry forward, but also all of the commitments that have been made in Glasgow recently and Paris earlier, helping to drive this forward. We really need to understand how to put the right policies in place to support this transition. And we need to definitely think what are other countries' strategies going to be alongside what we do ourselves. So my final slide is to cover the Heavy Industry Low Carbon Transition Cooperative Research Centre. We're very pleased to be participating in this centre, which will be up and running from early next year. It has $39 million of Commonwealth funding over 10 years. And significant contributions from all of the partners who are putting in their own cash and in-kind contributions. The three main parts of this program are process technologies, cross-cutting technologies, and then the policy, economic and social issues, as you can see there. So we're finalising our initial set of projects to give you a flavour of the sorts of things that we're going to be doing here at ANU. And before I talk about that, I should mention the CRC is being led by University of Adelaide, Professor Gus Nathan. The core partners who are basically the ones putting the most money in are the logos you can see there. There's a website with all of the other partners and more details. But yeah, back to the ANU topics. We're going to be putting most of our effort around this green steel or steel transition. We're going to be looking at hydrogen iron making, green process heat integration, hydrogen supply infrastructure, Scope 3 emissions accounting, economics and industrial policy, and novel iron making processes. And I wanted to reiterate how dynamic this whole space has been in the last year. We've seen net zero commitments from many of the companies on that list there, and they're very incredibly actively engaged with the CRC, but they're also doing a lot of parallel activities. It's really hard to actually keep up with all of them. The steel industry is several hundred years old, and many people say it's never been changing as fast as it is at the moment. So it's really exciting. Thanks very much.
Thank you very much, John. And that's a nice segue into the next presentation, which will be by Dr. Emma Aisbett. Emma is a fellow at the School of Regulation and Global Governance, otherwise known as RegNet, at the College of Asia and the Pacific. And she's also the Associate Director of Research at the Grand Challenge Zero Carbon Energy for the Asia Pacific. Over to you, Emma.
Thanks a lot, Ken, and hello, everyone. Lovely to see you all in person. Thanks a lot, Lamise. So I'm presenting, like Fiona and John, on behalf of a large number of team members who've worked for a couple of years now, thanks to a hot tip from Ken a couple of years ago and our great government contacts, that certification was going to be a thing in this space. And so a couple of years ago, we gathered a team and started busily working on this topic, and indeed it is a thing, a very big thing. So I have learned a lesson from my colleagues. I'm going to list names next time on my slides, but please let me at least verbally acknowledge Ken himself has been a very important part of this work, as has Lee White, who unfortunately couldn't be here because her cat's sick. Pen Howarth, one of our wonderful secondees to the ZKeep program, Alison Reeve when she was a secondee, and Fiona Beck has done a lot of the important calculations behind the graphs that I use in all of these presentations, and many more. So yeah, it's if you don't know the Zero Carbon Energy for the Asia Pacific Grand Challenge, we are a very interdisciplinary team, and this really, the certification work is, I think, where you see that most clearly. So perhaps for this audience, I don't need to say, but markets are increasingly wanting clean and green commodities. So as we've seen for the previous two presentations, hydrogen, ammonia, iron, aluminium, all of these things markets are wanting, but they, of course, they need to know if they're going to be paying a price premium, or in the case of a carbon border adjustment mechanism for Europe, letting our exporters not actually pay such a premium or a punishment for being dirty. They're going to actually want to know what the embedded emissions in those products were, and not just sort of take us on our word. And this is where embedded emissions accounting and certification really comes in. This is a very famous graph, by the way, that Fiona's calculations and Tom Longdon's wonderful graph making skills, probably some of you have seen this 10 times. So as Fiona said, hydrogen can be actually really dirty, and as Fiona also pointed out, it's not only the hydrogen that is made from fossil fuel reforming, so both gas and coal. Also, if you plug in an electrolyser to the existing grid, it can be even dirtier, and Matt Stocks is responsible for the calculations in this table, which would show you what Fiona's wonderful graph did, which is that it's even dirtier than making it by steam methane reforming. So we want green. We know that just using an electrolyser is not necessarily going to get us green. So how do we show to our investors, to our consumers, that what we've produced is actually green and or low emissions? As it turns out, I really can feel for John in his comment on trying to keep up with what's going on in the real world. Sometimes it can be very frustrating being here in academia, particularly when you get the second revision on some nitpicky detail on a paper, when you're working in this space that is moving so incredibly quickly. And what we are seeing is both public and private initiatives for certification schemes are popping up in multitude, both here in Australia and around the world. And there are a few problems that can arise from that, because not every certification scheme is going to be the same in important ways, and that means they won't necessarily be interoperable. So a couple of the key distinctions that are really relevant to the debate in Australia is whether you're certifying green or clean. Now, I've been using them synonymously here, but they are not the same thing. So green certification is usually when we're talking about 100% renewable energy being used to make a product, for example, hydrogen or ammonia. And this is, for example, the approach of the Smart Energy Council, who are leading sort of the major private or industry-led certification scheme for hydrogen in Australia at the moment. They're going for a zero emissions and green certification scheme. The federal government, Department of Industry, Science, Energy and Resources, have been working very hard internally, but also with other governments around the world, pushing really what you'd call clean certification. So they are big fans of a technology neutral approach to deciding what is sort of good enough to help us get towards net zero. And they're saying, look, it doesn't really matter what colour you call it or what the technology used was. What really matters is what ultimately the embedded emissions in that product are. And so when I say embedded emissions, I mean if I'm trying to sell someone a kilogram of hydrogen, how many kilograms of carbon equivalent emissions were emitted to make that kilogram of hydrogen. And so these are two very important distinctions that we're seeing in the emerging landscape of certification. There are many, many other dimensions as well. And one of the dimensions that our team worked on right at the start, in fact, co-authored with Penn and Fiona, was the question of boundaries. And so if you think about, if you know anything about carbon accounting, you would know that boundaries are a big thing. So where do you draw the lines of the system for which you're going to add up all the emissions? And so a lot of the certification schemes that are being developed initially are what's called a guarantee of origin. And so that's both the federal government's approach and the leading approach in Europe currently is to go all the way back to the well. So counting fugitive emissions that Fiona talked about, if you're using fossil fuels, up through the point of production of the hydrogen, but not going beyond that. And the purpose of this graph is to show that there are, in fact, a lot of important sort of major sources of emissions beyond that guarantee of origin stage. And so if you took a very sort of strong environmental focus, you would say, well, we need people to be making the right decisions, informed decisions all the way along the value chain. We can't just stop at a guarantee of origin. The problem for us in Australia is if these schemes in major markets have this approach of let's just do a big end-to-end supply chain certification system, that's going to be pretty hard for us who have half the supply chain in Australia and then a big ship and then it happens some more of the supply chain in Europe, and how do you add that all up? So our suggestion was to balance both these very important environmental drivers without producing non-tariff barriers to trade through certification schemes, was to take a modular approach to add up the supply chain emissions. And so that's our publication in Energy. So to conclude, certification is actually really complicated. The more I learn, the more complicated it is. There is a lot of competing approaches emerging, and that in itself can lead to excess regulatory burden for our producers of clean and green hydrogen. And so there's definitely an important role for governments to play in trying to get in and help with standardisation and lower that regulatory burden. So thank you all very much.
Thank you, Emma. And it's now my pleasure to introduce Margie Johnson. Margie is the CEO of the Australian Aluminium Council, and Margie joins us online from Adelaide. Over to you, Margie.
Not quite Adelaide, close, Queensland. But
Oh.
yeah. quite a long way away, but that's okay. And hopefully you can all hear me. We have some excellent Queensland weather going on today. And just as part of that, I would like to acknowledge the traditional lands that I'm on today, the lands of the Turrbal and Yuggera people, and I pay my respects to their elders past, present and emerging. So hopefully you can see my screen, and I'm going to give you a super quick overview of the industry. A bit like John, I've got to try and rush through mine to market really quickly, what we produce and where the main sources of emissions are. Whoops, that went up one. So Australia is one of the very few countries globally which has bauxite mining, alumina refining, aluminium smelting and aluminium extrusion here. Depending on the grade of bauxite, you need 4 to 6 tonnes of bauxite to make 2 tonnes of alumina to then make 1 tonne of aluminium, which can then be used for obviously a very wide variety of end uses, but also infinitely recycled. You can also see down the bottom of the screen the relative tonnages that we produce here in Australia and the value of the products we export. The further downstream you go, the much higher the value derived for that product. Looking at global demand, and as Emma said, you know, the world is demanding increasingly to understand more and more about their supply chains. Aluminium is a critical enabler of sustainable economic development, and its use is highly correlated with GDP. So as countries urbanise, per capita use of aluminium increases. Today, the global demand for aluminium is about 95 million tonnes, and about 2/3 of that is met through primary aluminium. That is aluminium produced from bauxite through to alumina through to aluminium. The International Aluminium Institute has done some modelling to predict, you know, requirements out to 2050, and their estimate is that it will need about a 40% increase by 2050. By then, even with the projected increased rates of recycling, still only about half the global aluminium demand will be able to be met by recycled aluminium, so the other half will need to be met by primary aluminium. That's good news for Australia. So that's going to require the bauxite, alumina and aluminium that Australia produces. And going back to the introduction, it's a question of how much of that can we do here in Australia. Equally, it's worth looking at, I guess, at the global context for the emissions that we had. And if you have a look there, we produce around 35 million tonnes of emissions across the sector each year. That's about 3% of the global industry's emissions, or about 7% of the Australian national emissions. I won't go into it in too much detail, but I would say if you're interested in how the aluminium industry is tackling the problems that Emma raised around certification, have a look at the details around the Aluminium Stewardship Initiative, which allows you to certify facilities, not on clean or green, but on a very large range of sustainability metrics that really look across the full spectrum of ESG. So, getting down into the detail of the emissions that the industry produce. The single biggest opportunity we have to decarbonise the vertically integrated industry is through decarbonisation of our electricity supply. So aluminium smelting produces most of the emissions at the moment. About 60% of the emissions in the industry at the moment come from the indirect emissions from smelters, so the electricity we use. But smelters are already fully electrified, so we don't need any new technology within the smelter for conversion. Also, really important to note that Australia's grid-connected bauxite mines, alumina refineries, and particularly our smelters are performing a really important enabling function in grid stabilisation, which is helping with the increased penetration of variable renewable electricity. What we see as the next challenge in the grid is how do we develop firming solutions at scale to help support even greater increased penetration of variable renewables. So while we often talk about aluminium, a very large part of the challenge is in fact alumina. And that's because most of the emissions for alumina are direct emissions. So Australia's alumina industry actually is already some of the world's lowest emissions intensity. So our emissions intensity here is about 0.7 tonnes per tonne compared to the global average of 1.2. So we're already starting from a great baseline, but there's of course always opportunity for improvement. So in terms of that, I'm going to duck in now to talk a little bit more about alumina, because that's really where I see the challenges are. And as was mentioned by John, we're partnering as well through my members, but also with the council directly through the HILT CRC, as well as partnering with government agencies like ARENA. So within the alumina refining process, about 95% of the current emissions, and they're 15 million tonnes a year, are direct emissions. Refineries currently use a mixture of coal and gas, depending on their location and historic access arrangements. So we actually in the industry usually talk around energy use rather than emissions. When we're looking at process technologies, it's easier to compare apples with apples across refineries. It's also worth noting that all of our alumina refineries already co-generate some or all of their electricity, which is otherwise a really obvious first step. So the Bayer process, which is used by alumina refineries worldwide, involves 4 steps: digestion, clarification, precipitation, and calcination. So the 2 most energy-intensive parts of the process are digestion. So as you can see from the sort of pie chart, that's about almost 2/3, just over 60%. So that is creating steam at 150 to 270 degrees. And then about nearly 1/3 is calcination. And that is where we need to heat the alumina precipitate to temperatures of over 1,000 degrees. So they're the 2 main energy processes. The industry is partnering on multiple pathways to look at what we can do and what alternate energy sources there are. So really, there's a couple of things we're really looking at. The main ones are electrification, to be able to see what parts of the pathway could be used, particularly looking to make electricity the primary part to replace the digestion. That's that nearly 2/3 of the pathway. So obviously, you could just swap existing electricity supply into and use electric digesters or electric boilers. They are currently available, but not commercially or viable. So you couldn't do that and still make money, and therefore you wouldn't make alumina. We're also looking at mechanical vapor recompression, which is a technology which uses mechanical compression to upgrade waste steam. So that technology is widely used in other industries, and Alcoa are currently trialling that in partnership with ARENA. The industry is also looking at ways in which the production and use of renewable hydrogen could be used in its process, particularly in calcination, because that might be the technology we need to get to those temperatures of over 1,000 degrees. Rio Tinto has partnered with ARENA to study whether hydrogen can be used in the calcination process. Additionally, it's possible that hydrogen could be used to replace gas in the boilers for digestion. That's seen as less likely at the moment. It would require a substantial capital retrofit and is less likely than direct electrification. We're the world's largest producer of alumina outside of China, so much of the global research into alumina technologies is being done here. Importantly, if successful, the technological and commercial lessons from these studies could be applied to the global alumina industry and other energy-intensive industries here in Australia. Thank you. I will try and stop sharing.
Yeah, I'll do it. Great, thank you, Margie, and apologies for being geographically challenged. It doesn't appear on the screen where you come from, so I'm glad you corrected
That's okay.
us. So I'm now going to invite my speakers to come up and join us here at the chairs, and we'll have an opportunity for Q&A. And with Chair's privilege, I'm going to start off the questions by asking one that was actually part of the discussion that we had earlier from Peter Ashworth with the question about hydrogen and water. So Peter was worried that in a dry country like Australia, that using electrolysis to make hydrogen from water was going to be an issue because we're water poor and all the rest of it. So maybe, Fiona, you could enlighten us as to whether this is going to be a problem or not.
Great, thanks a lot, Ken. So yes, we do need a lot of water to make hydrogen. Interestingly enough, you don't need that much more water to make hydrogen from electrolysis than you do to make it with coal or gas, and in fact, if you make it with CCS from gas, you need something like 14 litres instead of 9 litres that you need for electrolysis. So that's a lot of water. You could desalinate water in order to provide that, and the energy requirements are less than 1% of the total energy requirements that you would need. So what you could do is just factor that into your renewable energy. There is one other point to make, and that is that you've got to remember you also make oxygen. Oxygen actually ends up being a really useful thing for water processing, water purification, wastewater purification and treatment. So there is actually quite a synergy between making hydrogen and cleaning wastewater that is being investigated at the moment.
Great, thank you, Fiona, for that clarification. So the first question from the audience, I'm going to direct to Margie. So Margie, the question is, and a number of people asked this, can you comment on why aluminium recycling only reaches 50% of the supply by 2050?
Yep, I could talk for hours about aluminium recycling. Basically, aluminium doesn't corrode, which is excellent. Most aluminium, people think of aluminium as in packaging. So if you go to the shops, you buy a can of soft drink or beer, drink it, 60 days later, that'll be back on your shelf. However, aluminium used in packaging is only about 10% of the aluminium. Most aluminium is in use, is ever produced. More than 75 is still in use today. So it is still in the buildings. It's still in the wind turbines. It's still in the machinery, in the cables, in all the overhead cables. And that might be there for 50, 70 years. So it just takes that long before it gets to the end of its life. So that's really, even with really high recycling rates, you want the most efficient thing to do is to leave it there till the end of its life. And as I said, because it doesn't corrode, particularly on interior uses, it is basically can be used until the end of that building's life, which can be a very long time.
Great, thank you, Margie, for that answer. The next question is about green steel, and it's a very obvious question. If Australia cannot competitively make steel from its iron ore and coal, why should it be able to compete with its iron ore and hydrogen? John, maybe you'd like to start off.
Yeah, that's a very interesting question, and you know the iron and steel industry in Australia's had a lot of difficulty competing over the years, and we only produce 5 megatons per year of steel compared to our 900 megatons that we're exporting. So certainly we have to figure out if we can compete in this new world. So the most important point in our favour is the potential to benefit from the co-location of our iron ore with some of the best renewable energy resources in the world. The cost of the energy is such a big part of hydrogen iron making, and if you compare the solar resource on the east coast of China, where so much of the world's steel is made, with the solar resource in the Pilbara, the electricity cost is going to be something like 30% cheaper. That's if you're comparing solar with solar. Now, what we don't know is whether, you know, China might make a steel industry built around nuclear power, or they might put big HVDC lines across the continent. There's lots of other possibilities, and so that's where I think there's a huge amount of work to be done. Other issues are around the countries we're trading with and some of the implications on transport costs that come from transitioning this industry. Other factors are labour costs, and in Australia, our steel has a very relatively high labour cost fraction compared to many other countries in the world. Maybe as we transition to more automation, maybe that part could see change, and we might also recover a bit more of a competitive position through that. So I think there are a few things, and you know, I think this market, this whole area could change quite a bit, but yeah, we don't know yet how that's going to play out.
Yeah, I think the simple answer is really there are shifts in competitive advantages. Time and circumstances change, and it looks like many of these factors are changing. Maybe, Emma, you could say something about why other countries might wish to invest or co-invest in in green steel production in Australia.
Yeah, thanks. And I want to sort of second everything that John said. There's also maybe a clarification on the question. I wouldn't necessarily say our industry has shrunk because we couldn't compete, we weren't good enough. There are serious amounts of subsidies that go on into the iron and steel industries in all the major producers in the world. So one thing to watch is whether that continues at the same rate. And I think one of the things, if anyone's sort of watching the world today, is the geopolitical dimensions, and we're seeing obviously sort of tensions between Australia and China and competition between China and the US. So this also relates to the competitiveness or not of Australian hydrogen exports. I think a big factor to consider, and we will only see as time goes by, is the appetite to co-invest and trade with particular partners and a potential bifurcation of the global economy.
Good, thank you. So we now have another question about hydrogen, and this maybe is for Fiona. Is green hydrogen production suited to being a form of intermittent electricity demand, perhaps a way to soak up curtailed renewable power, or instead does it require dedicated baseload generation, i.e. renewable energy plus batteries, to be economic?
Yeah, that's a good question. So a large fraction of the cost of hydrogen at the moment is the capital cost of the electrolyzer and the balance of plant that goes along with that. So that means that if you're using essentially free curtailed energy, you're only running it 10% of the time or something like that. So that ends up being very expensive hydrogen then. So there is potential for a very large-scale hydrogen industry when we have, several 100% renewables on the grid. There is potential for there to be a bit of demand management that could happen in a renewable energy, in a renewable hydrogen industry, but really you want to be running your electrolyzer as much as possible. So the question as well between, whether you want storage in your system, electricity storage in your system to cover the periods where you're not producing renewable energy, or whether you just only produce hydrogen when the sun is shining and the wind is blowing is a one that's being very much studied at the moment. And I think it really depends on the cost assumptions you're using, because these are moving targets at the moment, all of them moving down, which is good. But also on where you are, what your renewable resource is like. It's worth noting that the big Asian renewable energy hub, where they're making large amounts of hydrogen, they're planning to make large amounts of hydrogen in the Pilbara. They are co-locating wind and solar to get the highest capacity factor they can out of their renewable energy system.
Good, and a very similar question for you, Margie, is can you explain how aluminium smelters can provide a grid balancing service? Of course, everybody knows if you turn off an aluminium smelter and leave it for very long, it becomes a big lump of aluminium, and there goes your smelter. So how does this work in terms of ramping up and down demand from smelters as a grid balancing service?
As you said, it's not an infinite grid balancing service by any stretch of the imagination. Smelters, around 75 minutes is really what you can lose power for before you start to get seriously worried. And you get more worried if it's an unplanned outage than if it's a planned outage. But what we've certainly seen, and Tomago is the most public example of this in terms of what they've done in New South Wales, but I would say we've seen it right across the grid in terms of all four smelters. Smelters have got incredibly good control systems in terms of the electricity they use. So they provide already a lot of the frequency control ancillary services, talking technical NEM terms now, which are the services from seconds through to minutes that can really help restabilize the grid, particularly when as it says, frequency goes out. And second of all, you can take off a pot line. So, and most smelters will have multiple pot lines. You can take those off for about an hour. And particularly if you know, as I said, if it's a planned outage, for example, you know it's going to be a really hot day and that the grid's going to become unstable later in the day, then the smelter will actually slightly pre-warm the pot line to preserve its thermal capacity so that you can drop load. But that means that you can drop loads of the size of 250 megawatts for an hour, and that's a pretty good resource to have in the system.
Yes, indeed. And just one final question, and probably this one is for Emma. It seems wise to modularise the supply chain for emissions accounting, but presumably those at the end of the supply chain need to be incentivised to buy green products earlier in the supply chain. How does that work?
Yeah, thank you for that question. So our idea is we calculate the embedded emissions within each sort of module in the supply chain, but that we set up a framework, and we're hoping very much that the ARC helps us work with government to do that, whereby you can add up all those modules across the supply chain. So if you're the end consumer, you're actually going to be seeing the certified total emissions for all of those previous modules from the well to your door.
So if you're in Europe and you're a bureaucrat dealing with the carbon border adjustment measures, all you care about is the total emissions intensity ascribed to the hydrogen once it's entering the border, which is a sum of all the previous emission modules.
That's an excellent question, actually. And the answer is, in the longer term, probably. For now, the European Emissions Trading Scheme only covers Scope 1 and 2 emissions, and that means that they are only allowed by WTO rules to look at Scope 1 and 2 emissions on the CBAM products as well. So just those last bits.
Very good. Well, I think that brings us to the end of the session now. We've had an excellent discussion on the prospects for the exporting of hydrogen and other green products from Australia, and particularly the implications of that for Australia's role as a heavy industry country, which not many people would necessarily think of us as, but we could become one yet again in the future. So thank you very much to our panellists, to Margie Johnson in Queensland, to Fiona Beck, John Pye and Emma Aisbett. Thank you all.